the engines here. Okay, good morning or good afternoon, everyone. And I'm very pleased to introduce today's Data Science for Wind Energy series speaker, Aziz Izzat from Rutgers University. Aziz is assistant professor in the Industrial and System Engineering department at the Rutgers University. Is the same in the same discipline as I'm in. I'm actually from a different discipline as from most of the wind engineering background folks here. But nevertheless, Aziz has been doing the wind forecasting research in the past number of years, and been introducing the AI type of method, data science AI method, to improve the offshore wind forecasting. Right? Today he's going to share his knowledge and their work about the AI-powered physics-based tool for the offshore wind forecasting. So without further ado, Aziz, the platform, the screen is yours.
Thank you very much, Professor Zink, for the introduction. Good morning, everyone. If you're in the US, good afternoon if you're in Europe. And my name is Aziz Izzat, and I'm assistant professor of industrial systems engineering at Rutgers University. And today I would like to present some of the work that we have been doing over the past couple of years in developing a tool for offshore wind forecasting and grid integration with specific geographical focus on the US offshore wind sector. So before I go into the content of my presentation, I would like to acknowledge the work of my research team. Many of the faces over there contributed to the development of this tool. So I oversee a research group at Rutgers University called the Renewables and Industrial Analytics Research Lab, or in short, RIA. And our ultimate goal is to develop solutions, particularly data science and operations research solutions, to address technical challenges in renewable energy. We are a group of motivated researchers from postdocs to undergraduate students. So a little bit of background on the offshore wind energy potential in the United States. So according to many reports, particularly I'm referring here to a report issued by the Department of Energy in 2016, the United States has significant offshore wind energy potential. In fact, the technical study suggests that this potential can be more than 2,000 gigawatts, which is double the electricity consumption of the United States. And this offshore wind potential is distributed across 5 major geographical regions: the US East Coast, the West Coast, the Gulf of Mexico, the Great Lakes, and then there is the North Atlantic and the Mid and South Atlantic regions. The US East Coast in particular is or expected to be the first and largest contributor to the US offshore wind potential for many reasons, particularly related to the bathymetry of the seafloor there, enabling fixed bottom offshore wind turbines to be installed. There are obviously with any new renewable energy industry, particularly in the US, there are a number of challenges. Here we primarily focus on the wind forecasting challenge. As many renewables, offshore wind relies on accurate forecasts of the hub height wind resource and the power output in order to ensure the efficient and reliable operation of the offshore wind farms. And a couple of particular challenges that are related to this need for a wind forecasting tool is the fact that there are very sparse and scarce measurements, hub height measurements available in this region, particularly the US East Coast. So when I say sparse, I mean that there is fairly limited time coverage. So we're talking about the measurement campaign started going there in 2019 and later. So there isn't long historical records at altitudes relevant to the hub height, but I'm also talking scarce measurement in terms of spatial coverage. So we typically have those LiDAR buoys installed at specific locations that do not provide a full coverage of what the wind conditions are at the full spatial sites. And then the fact that there aren't sufficient coverage over space and time for these measurements leads to the fact that all the numerical weather models out there are typically undervalidated. The goal of this project, which kicked off in September of 2023, was to develop a forecasting tool that we dubbed as AI RUWRF. The goal of the tool is to combine region-specific weather models together with machine learning technologies in order to produce superior offshore wind resource and power forecasts that are practically unattainable using the weather models alone, and are hopefully more superior than just using data science models. So the goal here is not to replace numerical weather model, but rather to build on top of numerical weather prediction models using data science capabilities. A particular or a unique focus of this project is once this tool is developed is not only to evaluate the benefits of AI RUWRF in terms of how accurate the forecasts are, which is the forecast quality or accuracy, but also in terms of how much economic benefit can potentially be achieved if this or the forecasts from this tool are used in operating the offshore wind farms. So this is a multi-institution effort. Leading the project is Rutgers University. And by the way, the project just concluded in June of 2025. So we're in the process of writing the final report at the moment. We have Rutgers University, and within Rutgers University, there are two research groups that are working on this. My research group in the School of Engineering, bringing data science for renewable energy expertise. And then there is the Rutgers Center for Ocean Observing Leadership within the Department of Marine and Coastal Sciences, which brings a lot of meteorological and oceanographic knowledge into the development of our tool. We are collaborating on this project with the Center for Electric Power System Research at Clarkson University, particularly to accomplish this step related to the economic value of using the improved forecasts into power grid models. And then we have also the Electric Power Research Institute, EPRI, who are bringing in years of expertise in the offshore wind space. The project also has an multi-stakeholder advisory board representing power producers as well as state and federal agencies. Before talking about AI RUWRF, I'd like to talk about a background technology that existed at Rutgers University, and this is where consisted the background knowledge on top of which we built our model. The background technology is a model that has been developed at Rutgers about 10 years ago called RUWRF. And if you've done forecasting work or resource assessment work, you may have used WRF. WRF is short for the Weather Research and Forecasting Model. It's one of the regional or mesoscale numerical weather models that are typically used for forecasting purposes and resource assessment studies. Over the last 10 years, Rutgers University developed its own variant of WRF called RUWRF, Rutgers University WRF model. And it's basically a WRF model, but then the parameterizations of this WRF model has been particularly tailored and fine-tuned to better reflect the physical phenomena in the US East Coast. And it has also been tailored to particularly address the needs of the offshore wind industry in this particular region. So it has three main regional focuses. There is the 1 kilometer resolution, the 3 kilometer resolution, and the 9 kilometer resolution. It also produces multi-height outputs across the whole swept area of the expected offshore wind turbine hub height from 40 meters up to 260 meters. The grid points of RU-WRF has also been pre-selected to basically reflect the centroids of the offshore wind energy areas in the US East Coast. So this is the technology that we have been building on top of. And RU-WRF, through a few studies, one of which was independently validated by NREL, the National Renewable Energy Lab, has been shown to outperform other numerical weather products that have not been tailored to this particular region. So for example, comparisons against HER shows that the RU-WRF significantly reduces the model bias at specific locations where offshore wind farms could potentially be built. Since we have RU-WRF as input to our model, our goal in this product is to build on top of RU-WRF in order to add a layer of machine learning or data science in order to further improve what RU-WRF produces. And then the goal is to hopefully produce forecasts that are of higher resolution than what is produced by RU-WRF and of higher accuracy than those produced by RU-WRF. So generally, AI RU-WRF, the data science model, takes as input two main sources of information. We have hub height wind measurements collected from multiple floating LiDAR buoys that have been deployed in the US East Coast. And then it takes numerical weather predictions coming from RU-WRF. There are three main modules. I'm going to quickly go over them now, but then in the next 3 slides, I'm going to present one slide per each module to present the high level of what each of those modules are. The first module is what we call an NWP downscaler. So NWP stands for numerical weather prediction. So the goal is to correct the bias of numerical weather predictions. Once you downscale the numerical weather predictions at resolutions that are relevant to a single turbine or a single wind farm, we start observing some significant biases for numerical weather predictions. And the goal here is to correct those biases by bringing them closer to the hub height wind measurements. The way we do this is through a regression model that has specific terms for additive and multiplicative biases. I'm going to speak about that in a minute. But then it's basically a regression model that regresses the numerical weather prediction outputs on the hub height measurements in order to bring those numerical weather products closer to the hub height wind measurements. Once we are done with this step, which is basically the output of this step is basically a corrected numerical weather prediction output, we have a layer of brute force machine learning where we have a model that takes as input the hub height wind measurements as well as the corrected numerical weather predictions, and then tries to learn something about the patterns observed over time, and then as well as the correlations that exist between the different hub height measurements observed at multiple locations. And the output of this step are 3 things. And this is one thing in particular that motivated our choice of the modeling. And I'm going to speak about that in a minute. The outputs expected, first of all, you obviously have the time series of the wind speed forecasts. So this is what you expect out of any forecasting model, right? Time series of what the hub height wind speed conditions are expected. But then we are also able to produce spatial wind field forecast maps. So not only producing predictions at specific locations, but rather obtaining a spatial wind field forecast map that can be potentially used to inform what the spatial behavior of the wind conditions are. And then most importantly, we also obtain a probability distribution for the wind speed forecast. So not only a point or a deterministic forecast, but rather a full characterization of what the probability distribution of the wind speed conditions are. Once this step is done, we go to the third module, which is the power predictor. And this is where we do the wind to power conversion, right? So far we have produced forecasts of the wind speed conditions. And then we take as input here weight corrected wind power curves. And then the goal here is to convert probabilistically the wind speed forecast that we have obtained from module 2 into wind power prediction. And you see here that I have repeated the word probabilistic multiple times because, again, the goal is not only to obtain time series of wind power forecasts, but also a full probabilistic characterization of what the wind power distribution is expected to be. And from that wind power predictive distribution, we issue something called the probability of exceedance, which I'm going to speak about as it's a critical input to the economic analysis that we have conducted in collaboration with Clarkson University. So in the next 3 to 4 slides, what I'm going to do is I'm going to provide a high-level overview of each one of those modules. And then from there, I'm going to spend the majority of the time of this presentation to provide key highlights of the results that we have obtained from our forecast evaluation studies, as well as from the economic analysis piece. So the numerical weather prediction downscaler, or the NWP downscaler, as I mentioned, the goal here is to take as input the numerical weather predictions and then correct the biases that you start to observe once you start downscaling those numerical weather predictions. And here I offer just 2 examples, 2 snapshots from 2 different days, November 7, November 21 from 2019, to demonstrate what kind of bias do we observe once we start downscaling the numerical weather predictions at the resolutions at which the forecasts are made. When we tend to think about bias, we tend to think about what I call here the shift bias, right? Which is typically a consistent over-prediction or under-prediction of what the wind conditions will be. So when you look at this figure over here, this is the hub height wind speeds at 140 meters, and this is the time in hours. The numerical weather prediction, this is the output from RU Wharf. These are the red triangles over here. And then the measurements, those are the hub height wind conditions that have been observed through the buoy that has been installed at a specific location. And you can see that RU Wharf actually does a very decent job in capturing the overall trend of how the wind conditions evolve over the day. However, there are some noticeable biases, some of which are a consistent over-prediction or under-prediction of the wind conditions for a consistent period of time, but there are also other types of biases. So shift bias is one type of bias, but then there is timing bias as well. Sometimes the numerical weather prediction would predict the value correctly, but then it would predict it 2 hours late or 2 hours early. And this is common in numerical weather prediction outputs. And then there are also multiplicative biases that are typically driven by interactions between the different meteorological drivers. So this is just one equation here that shows the high-level idea of what this numerical weather prediction downscaler is. It's basically a regression model. But then it's a regression model that takes as input the numerical weather prediction outputs. So this is what the wind speed forecasts of RU Wharf are, but then it takes as inputs as well some additional features that we think are potential predictors of the numerical weather prediction bias. And then there are sets of parameters here, A, B, and C are vectors of parameters that we estimate through this regression formalism in order to bring the numerical weather prediction models closer to the hub height measurements that we observe. There's a lot of work that went into what features go into this regression form. Primarily, those are other outputs from RU Wharf, numerical weather prediction outputs, other than the wind speed predictions. The way this works is that it's kind of like a dynamic regression model, wherein at every forecasting time step, what we do is that we stop, we think about what features have relevance in correcting the bias of numerical weather prediction models, and then we select those features as part of the model. So once we have corrected the biases of the numerical weather prediction models, the next goal is to apply the machine learning based the forecaster. This is the second module in the overall flowchart that I have shown. And this is a machine learning model that directly acts on the hub height measurements in order to extract temporal patterns as well as the correlations over time and space. So here in this figure over here, I'm showing you a sample time series for a few days in November of 2019. This is the hub height wind conditions at 140 meters. And EO5 and EO6 are actually two floating LiDAR buoys that are approximately 70 kilometers apart from each other. And those are located very close to the offshore wind energy areas. And once you look at those time series, you immediately observe how similar they are, right? The wind conditions are very similar, even though they are 70 kilometers apart, but the hub height wind conditions are very similar at EO5 and EO6. And this further motivates their joint modeling, right? So instead of building a separate model for EO5, a separate model for EO6, you'd like to build a model that does some sort of knowledge transfer between the time series observed at EO5 and the time series observed at EO5. There are many ways how you can model these time series jointly with each other. One way we have done this is through a machine learning model called a Gaussian process model. And the Gaussian process model are machine learning models that are typically suited to model correlated data. So when we have correlated data either over time or space, Gaussian process models comes as a handy machine learning model to model the correlations in time and over space as well. And one particular advantage of Gaussian process models is that they are probabilistic models, meaning that the outputs of Gaussian processes is not only the deterministic or point predictions of what the wind conditions are going to be at EO5 or EO6, but rather a full probabilistic characterization of what the wind conditions are expected to be. Gaussian processes are kernel-based models. So there's a branch of machine learning models. One branch of machine learning models are kernel-based models. Those are models that use the idea of a kernel to model correlations. Another example is support vector machines, also a kernel-based model, for example. Gaussian processes is a kernel-based model that uses the idea of a kernel in order to model the correlations over time and space. And there are different choices for how we model this kernel. There's a lot of work that we have spent into building a kernel that actually reflects the wind conditions observed at EO5 and EO6. Typically, the kernel function is a parametric function that models the correlations as function of the time or the spatial separation, with the general intuition that if two observations are closer to each other in time, they tend to be more similar. And if two observations are closer to each other in space, they tend to be more similar. And that's basically how a kernel function works. And we have put in a lot of effort to model a kernel function that can accurately capture the spatial and temporal trends accurately, and that actually takes as input the numerical weather predictions as part of the inputs into that kernel function in order to inform or invoke some sort of a directionality into the correlations between the different time series observed at different locations. So once we have the second module done, as I mentioned, the ML-based forecaster outputs wind speed forecasts. The goal at the end is to translate those wind speed forecasts into wind power predictions, and to do so not only deterministically, but also probabilistically. So we start with a wind speed forecast distribution from the ML-based forecaster of AI Ariworth. And then we have also a model for the wind power curve, the relationship between the wind speed and wind power, modeled probabilistically. And then we apply a very simple trick. Our goal here, this is what I'm showing here is a variant of the law of total probability, right? So one of the main rules of probability that governs how you obtain a probability distribution from a conditional distribution. So if we have the power curve, right, that's the probability of the wind power condition on the wind speed. And then we have the probability of the wind speed coming from AI Ariworth forecast. Then if you integrate over this, you get the wind power forecast distribution. And then what we do is basically approximate that integral through a Monte Carlo approximation. So what we do is we just sample many scenarios of wind speed from the AI RU-Whorf model, and then from there we compute the predicted distribution of the wind power through a Monte Carlo approximation. So one major advantage of this is, as I mentioned, is to obtain a closed form expression for the wind power distribution, not only the deterministic or point predictions at specific locations or specific times. So in the next few slides, I'm going to show some key result highlights that we have obtained from training and testing AI RU-Whorf on multiple locations and multiple time periods. So we have data coming from 3 buoys, EO5 North, EO6, and Atlantic Shore. This is the US East Coast, right? And this is New York, and this is New Jersey, where Rutgers University is. Those areas over there are the offshore wind energy areas that could potentially be developed into offshore wind farms off of the US East Coast. When you look at the bottom figure over here, this is a map that we have prepared that actually shows all the buoys that have been deployed in this region. So those are the locations where you have measurements. And then the 3 colors up there denote data availability. So a green color means data available for the majority of the month. So for example, February 2020, it means that we have the majority of the data available there, maybe few missing points here and there. Orange means intermediate or medium availability. Maybe we have half of the month of data availability, something like that. And then red means no to very little availability of data. And once you observe this, you immediately see a problem for any machine learning model, right? We have very scarce and sparse data availability for the different locations, right? And the one challenge is that not only about the data quantity, but also in order to build a machine learning model, you need data availability simultaneously at multiple locations, right? In order to characterize these correlations over space and time, you need simultaneous data coverage at multiple locations. And this is something that we don't have the luxury of. Perhaps only happens for 3 locations at once at specific time periods. And that has significantly limited both the choice of the models that we have been developing, as well as the amount of training and testing that we can do on the models themselves. So we were under significant data constraints. But I believe that that also adds value to the kind of research we do. And that is one of the main reasons why there isn't so far solutions that are particularly tailored for this offshore wind energy areas. So the training of the model ranged from 1 week to 3 months. And here I'm speaking about the data size for training. So we typically, our model takes anywhere between 1 week up to 3 months of historical data in order to train and produce forecasts. And then we tested our model on a rolling forecasting basis. So we train the model, we forecast for 24 hours ahead, and then we roll or slide by 1 hour, and then repeat the whole training and testing procedure, and then slide for the whole 6 months. We have evaluated our models using 2 evaluation criteria: mean absolute error, as well as the continuous rank probability score. One of them is a point or deterministic evaluation metric. The other is a probabilistic metric that looks into the probability distribution output of AI RU-Whorf. We have compared against time series models, against deep learning models, against physics-based models, the Bayes numerical weather predictions, as well as the corrected versions thereof. So in the next few slides, I'm going to show glimpses or kind of like snapshots of the key highlights that we have obtained. In the earlier phase of this project, we have primarily focused on short-term forecasting. And by short-term forecasting here, I specifically focus on forecast horizons ranging from 10 minutes ahead all the way till 6 hours ahead. So on the x-axis over here, for example, you see the forecasting horizon, how far ahead you're trying to forecast, starting from 1 hour. So this is the average of the first hour, all the way till 6 hours ahead. One of the, and here we only show a subset of the comparisons. If you look at the forecasting performance here at one of the key locations, EO6, you find, for example, a data-driven model like ARIMA. This is a time series model that takes as input the historical observations and then extrapolates them into the future. You see that time series model that are purely data-driven perform really well at short-term horizons. But then the forecasting performance quickly degrades as the forecast horizon extends. Whereas the Bayes numerical weather prediction model, like RU-WRF, kind of produces consistent forecast errors across the full forecast horizon and overtakes the data-driven models at around somewhere between 3 to 4 hours. AI RU-WRF, because it's a hybrid model, it's not a purely data-driven model, it's not a purely physics-based model. It takes as input RU-WRF and then corrects it using a data science layer. It's able to produce forecasts that are better than the data-driven models at the short-term horizon and consistently, or at least maintains an improvement margin over RU-WRF as the forecast horizon extends. You can see here that the forecasting margin or the improvement margin over RU-WRF kind of diminishes as the forecast horizon extends. And this is one of the reasons why the earlier phase of this project particularly focused on the short-term forecasting, since as the forecast horizon extends, the margin of improvement of AI RU-WRF starts to diminish. And we have addressed this challenge in the later part of the project, and I'm going to show some slides related to that. But in addition to the average forecasting error, you can see on the right side over here some interesting results that we have obtained. So in the bottom figure, you see here the actual wind speed predictions versus the forecast wind speed predictions from AI RU-WRF versus those from RU-WRF, the Bayes numerical weather prediction that is used as input for AI RU-WRF. And you can immediately see that because of that NWP downscaler, where we have intentionally tried to correct the biases of numerical weather predictions, that the predictions from AI RU-WRF versus the true values are clustered around the 45-degree line, indicating a very small bias in prediction, whereas that from RU-WRF has a significant density of the points above the 45-degree line, especially as the wind speed values increases. Another major advantage of AI RU-WRF is ability to produce probabilistic information. So you can see here in the bottom figure that not only we are able to produce the expected hub height wind speed forecast, but also prediction intervals that can provide probabilistic context for the users of these forecast outputs. Another advantage of AI RU-WRF is its ability to produce forecasts at any location, even at locations where no measurements are available. So here, for example, I'm showing the polygons over here represent the offshore wind energy areas where offshore wind farms could potentially be developed. And then the two stars over here denote the locations at which measurements are available. And then the advantage of AI RU-WRF, and particularly due to the ML-based forecaster module, its ability to extrapolate what has been learned at these locations where measurements are available at other locations where no data is available. And we think that a trait or characteristic is particularly useful for the offshore wind industry in the US, for example, where not a lot of measurements are available. So you're kind of capitalizing or leveraging what you have in order to extrapolate at other locations. So the background heat map you see over here, those are the outputs from our model. Obviously, we can only validate it at the locations where measurements are available. So what you see in the bottom figure here are the time series predictions at EO5 North, one of the locations where we have measurements, but then we're able to also extrapolate those at locations where no measurements are available. And this is what we mean by a spatial wind field forecast map. And then obviously our ability to produce prediction intervals, as I mentioned, and then the fact that we have full characterization of the wind speed distribution enables us to generate also scenarios of wind speed predictions that could potentially be used for different operational contexts. And the outputs from this study has been published in Renewable Energy in 2024. Once we have finished that phase of the project, we have started thinking about how to extend the forecasting advantage of AI RUWRF beyond the 6 hours. As you have seen in the previous figure over here, as the forecast horizon extend, the advantage that you have from AI RUWRF diminishes relative to the base RUWRF model. And we wanted to think about solutions in order to maintain an advantage of AI RUWRF up to 24 hours ahead. So we've had a few solutions targeted to that, one of which was a seasonal solution. And by seasonal, I mean a solution that worked only for specific seasons in the US East Coast. So the US East Coast, as similar to some locations around the world, experiences a particular physical phenomena called coastal upwelling. And coastal upwelling, and I'm not an oceanographer or a meteorologist, but my understanding of coastal upwelling is that it's a situation when you have along the coast winds, so winds that are parallel to the coastline, that basically causes the warmer surface water that is closer to shore to move farther offshore, and it then gets replaced by deeper and colder water, which rises from bottom to replace the water that was pushed away. So what is the relevance of this for offshore wind? This is, by the way, a very relevant oceanographic process related to obviously sea surface temperature and related to all the ecology and the fishing that happens in the coast. But then it actually, recent evidence suggests that it has some implications on the offshore wind industry because of the interactions between the air and sea surfaces. So once you have those dynamics of air-sea interactions, it actually impacts what the hub height wind conditions are expected to be. What you see on the right-hand side here is a calendar that shows in summer 2020 how many of the days experienced upwelling. And this has been developed by our collaborators in the Marine and Coastal Science Department, where they have developed a simple algorithm that looks into satellite imagery and then tells you whether coastal upwelling is active or non-active. So we've done some analysis on that, and again, using the data from the 3 buoys that we have over here. So you can see the difference between figure A and figure B is that in figure A, you have coastal upwelling active, versus in figure B, you don't have coastal upwelling active. The heat map over here is the sea surface temperature. And you can see that in figure A, there is fairly observable shore to sea or coast to sea temperature gradient, thermal gradient, whereas here temperatures look much more homogeneous than in this figure A over here. When you actually study the difference in wind speeds between when upwelling is active versus non-active, you can see that there is an observable difference between the wind speed distribution when coastal upwelling is active versus when coastal upwelling is not active. You see this in the difference between the wind speed medians, but you also see a difference in the spread of the distribution as well. And this difference gets even more amplified once you convert those wind speed differences into wind power differences because of the cubic wind to power relationship. And you can see that the wind power distribution when the upwelling is active is actually significantly bigger than that when the coastal upwelling is non-active. So the way we address this from a data science perspective is using a very simple idea called regime switching. And regime switching is a very simple idea, which basically dictates that I'm going to build separate models for when the upwelling is active versus when the non-upwelling is active. So it's exactly the same model, but then the model is trained on data that is specifically relevant to when the upwelling is active versus non-active. And how do we know whether the upwelling is active or not? Using the same algorithm that our collaborators has developed from satellite imagery. So you look at the satellite imagery at the time you're trying to make forecasts, you determine whether upwelling is active or not, and then from there, you decide whether to invoke the model that has been trained for upwelling conditions versus the model that has been trained for non-upwelling conditions. Now, our experiments actually show that once you extend the forecast horizon beyond 24 hours, this idea, particularly for the summer seasons where the coastal upwelling is active, enlarges or augments the improvements from AI RUWRF relative to the Bayes numerical weather prediction output, especially at locations where upwelling is active. At Atlantic shore is closer to shore. The ASOW4, that's a buoy that is closer to shore, and hence the improvement obtained from such the integration of upwelling information is more prevalent. Okay, so this idea of a regime switching was particularly useful for the summer seasons where upwelling is active, but it was not as effective in other seasons where upwelling was not active. So we needed to take a more drastic change in how the model is developed. And I think we came at the intuitive conclusion that in order to produce forecasts that have significant value up to 24 hours ahead, you need to zoom out. You need to think about what happens at the broader meteorological landscape of the locations that you are trying to make forecasts at. Previously, what we have been doing so far is only to look at the locations or observations where we would like to make forecasts. But then in this part of the project, what we decided to do is actually to zoom out and then start thinking of using information from the larger scale meteorological landscape around the locations where we try to make forecasts. So we did some clustering analysis where we have taken actually a fairly large geographical area, 300 by 300 kilometer squared region, about 100 grid points from numerical weather prediction model. And then we did a clustering analysis where we input the wind vectors and the air pressure. And then we output the between cluster pressure gradients. And then we output a number of other meteorological features like pressure gradients, as well as other large-scale meteorological descriptors of the spatial domain. And then we use that as input to the AI RUWRF model. So it's basically the output of this analysis is an augmented set of descriptors or features that go as inputs to AI RUWRF. And from there, so for example, what you see in the top left figure over here, that's one of the descriptors that we output from the cluster analysis. That's the pressure difference across this large geographical region. And you can see immediately that there is some decent correlation between that pressure difference and between the hub height wind speed conditions that we would like to predict. From there, we actually developed two variants of AI RUWRF. The first variant of AI RUWRF is what I showed earlier, is only tailored to produce forecasts for 0 up to 6 hours ahead. And then the second variant of AI RUWRF is very similar in model architecture, but then it takes as input those additional large-scale meteorological features that we have obtained from the clustering analysis. Another difference between the second and the first variant of AI RUWRF is that the second variant is uses more training data size. So for the short-term model, the one that is tailored for the 0 to 6 hours ahead, we only use 7 days of historical data, whereas for the version 2 of the model, we use up to 60 or sometimes 90 days of historical data. And then what you end up with is basically two variants of the model, right? What we call AI RUWRF short, that is particularly tailored for the short-term horizon, and then AI RUWRF long, which is particularly tailored to longer forecasting. Here by longer forecasting, I mean day-ahead forecasting. And then you end up with two separate models, right? And the question becomes, how can you combine these two separate models into one forecast? At the end, we need one forecast output, right? So we thought about the idea of an ensemble forecast. So we're going to build the two separate models for based on AI RUWRF, one that is specifically tailored for short-term horizon, one that is specifically tailored for long-term horizon, and then we are going to ensemble them together. So this is what you see here in the left figure. This is an example from one day in June 27 that is representative of many of the days that we have observed. What happens is that the short-term model typically it does reasonably well in the short-term forecast horizon. So this is about 0 to 12 hours ahead, right? So you see here that blue, the output from that blue model fairly matches with the observations. And then as you go farther into the future, the long-term model becomes more closer to what you observe in reality than the short-term model. Obviously, it's not consistent across every hour of the day. So for example, here it happens that the short-term model performs reasonably well. But generally speaking, on average, what you see on the right, for example, this is the average performance across the 6 months of data. And you can see that the long-term model performs only better once the forecasting horizon extends beyond maybe 6 hours or so, whereas the short-term model performs really well in the first maybe 0 to 4 or 5 hours, and then afterwards the performance degrades as the forecast horizon extends. And then the idea is, how can we come up with this golden ensemble, right? So this is the ensemble of 2 models coming from the short-term model and the long-term model using a special weighing function. A few considerations that we have considered is, first of all, the automation, meaning that you want to combine those. You want to combine those in a way that is not arbitrary, right? So I don't want to say, for example, I'm going to use the first model up to 5 hours and then the second model for anything after 5 hours, right? Because that threshold by itself is dynamic. Sometimes the short-term model performs well up to 2 hours and sometimes perform well up to 9 hours, right? So you need this dynamic approach to weigh these models. And you need it in a way that is informed by the data itself. And another important consideration is that when you do that ensemble, I would like to preserve the probabilistic information. The short-term model output probabilistic information, the long-term model outputs probabilistic information. I would like to reach a forecast that preserves that probabilistic information when doing the ensembling. So we came up with an algorithm to do so, and I'm not going to go over the algorithm. It's but although, like, if you skip the details, it's actually pretty simple. You build the short-term model, you build the long-term model, and then you do the ensemble, right? Those are basically the 3 steps. But then the key idea of the ensemble here is that it's a time-dependent ensemble, meaning that the weights given to the short-term model and the long-term model are function of the forecast horizon, and those weights are tuned in light of the historical data. So every time we train the model, we look back into the past and then determine up to time t what is the best weight that we can use to ensemble these 2 models together. There's also some work that went into the probabilistic information because, as I mentioned, we need to output a probability distribution out of that. So when we're doing the ensemble, you need not only to look at the expected predictions from each of the short and long-term models, but also look into their probabilistic ensemble together. So some key results that we have obtained over here. So this is the average performance across the forecast horizon. And you see here 4 models comparisons. The red and blue models are the long and short-term models respectively that we have developed. And then the green is the numerical weather prediction model that's coming from RUWRF. And then the purple is the ensemble model that's coming out of the ensembling of the short and long-term models. Again, you can see the trend that in the short-term horizon, the short-term model performs reasonably well, whereas somewhere around 6 hours, the long-term model, which is the red circles over here, overtake the short-term model. And then the ensemble, because it kind of reconciles the best of both worlds, it's able to produce forecasts that are better in the short term and better in the long term. The evolution of these ideas obviously were not linear, in the sense that we hit first the bottleneck of the short-term model, and from there we started thinking, how can we change AI RUWRF to produce better predictions? We came up with the long-term model, and then we wanted to reconcile those 2 sets of approaches, so we invoked an ensemble forecast. Generally speaking, we see improvements anywhere between 3 to 5% over the short and long-term model across the full day-ahead prediction. We observe improvements about 7% relative to the Bayes numerical weather prediction models. And then we observe significant improvement over all the data-driven models. Those are all data-driven models. Like when we train an LSTM or an ARIMA-X, we train it without the numerical weather prediction inputs. And while they are very competitive in the short term, like maybe 0 to 2 hours ahead, their performance significantly degrades once you go to the day-ahead predictions. The model, the ensemble model, the output is able to produce prediction intervals. As you can see here, this is a snapshot for 1 week in May 2020. It's fully probabilistic. And because it's fully probabilistic, you are able to also produce scenarios of, for example, here, wind power. So these are what you see over here are wind power scenarios obtained from AI-RU-WRF that could potentially be used in operational context. We are wrapping up this paper at the moment, and then as part of that, we're going to also make all the codes available. So, I think we're about how much time do we have left?
I don't know how many slides do you have left.
No, I think here I can skip this part. It's although I can just in the next maybe
it's probably better to leave some time for discussion. For
I agree.
Folks have questions. We usually like to wrap up exactly on the hour. We know we start a few minutes late, but other folks has things planned to do beyond the hour. So if we can finish it at the hour, that'd be the great. Yeah.
Definitely. So just I have about 4 or 5 slides on this economic evaluation. But instead of going through every detail of that slide, I'm going to primarily or maybe focus on conveying the message of this part of the project. This part of the project was led by our collaborators at Clarkson University at the Center of Electric Power System Research. And the goal of this part of the project was not only to stop at how accurate the forecasts are, but further think about how much economic value can these improved forecasts bring into the offshore wind industry. So, and this was one of the main aspects that led us to think about models that can output probabilistic information from the forecast. Because once you have a probability distribution, you can output important probabilistic statistics and outputs. One of which is obviously the scenarios that I showed over here. So ability to simulate scenarios of what the wind power could be in the best case scenario, in the worst case scenario, and so forth. But also you can compute things like the probability of exceedance. What's the probability that wind power is going to be greater than or less than a particular threshold? And we have used this POE as inputs to a reserve procurement methodology that has been developed by our colleagues at Clarkson University that mimics how power grid operators procure reserves. And then we particularly focus on the offshore wind energy areas in the New Jersey, New York region. And then we show that the improved forecasts can in fact reduce the amount of reserves that the power grid operator needs to procure ahead of time because of that improvements in forecast accuracy. So we compared, for example, AI-RU-WRF against the Bayes model, RU-WRF, and against the persistence model as a benchmark. And we show that the economic implications of using improved forecast can indeed lead to significant improvements in procuring the reserves for power grid operation. Okay, so I think I'm going to conclude here. So the main crux of this presentation is that we have developed AI-RU-WRF. This is a data science model that is tailored to the offshore wind energies in the US East Coast. We have tested AI-RU-WRF on 2 fronts: forecast accuracy, which is how accurate the forecasts are, as well as forecast value, how much economic savings can potentially be accrued having used the improved forecasts. Some ongoing questions that we are currently reflecting on. So even though the project has officially ended, but we obviously this is a direction that our lab is pursuing. So there are some immediate goals related to obviously publishing some of the outputs already published, but particularly publishing that last piece of AI RU together with the codes of AI RU. But then we obviously, in order to confirm many of those conclusions here, we need more testing. As I mentioned, data scarcity was a problem or was a challenge in developing and testing AI RU. We are thinking about the possibility of using the emerging Gen AI techniques to help overcome some of those data challenges. I can certainly speak to that if there's interest. We are thinking about how to account for wakes. So recent evidence suggests that there are long interfarm wakes. So far, we have only used free wind measurements, right? And then how to operationalize AI so that it actually can be used in practice by the offshore wind developers. So acknowledgement for the National Offshore Wind Research and Development Consortium who supported this project. There are multiple publications. Some of them have already been published. Some of them are under review or working papers. And we also have one data set that has been already published, which is basically all the data that we have been using for training and testing the models. We have also output the forecasts from our model, all in a time series format. This was published in June 26, 2025. And it's available on a data repository on Zenodo. So if you're working in the forecasting space, I think this could be an additional data set to benchmark your models and possibly even compare your models against ours and see if there are any areas of collaborations or improvements that we can pursue. And then the final full codes of the model will be publicly available upon the publications of the final day-ahead model. So with that, I conclude my presentation. Thank you very much, Hugh, and thank you for the audience for listening.
Well, thank you very much, Aziz, for the very insightful talk. You probably, I'm not sure if you're aware of, there's a colleague, he sometimes come to our forum too, Alex Clerk from RES. I probably pronounced his last name wrong. He's running kind of wind forecasting, wind power modeling competition on a different platform. I probably can find that information in case you didn't notice that. I think the deadline is still a couple of 1 or 2 months down the road. Seems to very relevant to what you are doing here. If you are, your team has the bandwidth, you might want to take a look of that.
Definitely, yeah. Thank you.
So we have 1, 2 minutes left. I know other folks probably have other plans, but if you have a few more minutes, you are welcome to stay since we're going to be here just for a few more minutes beyond the hour. So any questions from the audience? Okay, Aziza, I have a clarification question on your slide number 6.
Here?
Yeah, so this 40 meter to 260 meter, did you mention this as 260 meter is a hub height?
No, 260 meter is the tip
The
of
tip
the blade.
oh, okay.
Yes.
Okay.
Oh, yeah.
I figured there's no that large wind turbine yet in the offshore of United.
Yeah. So for our training and forecasting experiments, we have been using the 140 meters as
140 meters.
Yeah.
Okay. So here you are doing the forecasting by separating the power curve versus the wind speed forecasting, right, in two steps. There's always a debate. The debate probably lasting for like in the past 30, 40 years, right? I don't think that there's a settled yet. It's like some people said you should really do a unified forecasting with all the kind of input without explicitly modeling the power curve, and then simply just do the forecasting on the power. And some other people said, since the physics are different from the wind forecasting and the power curve conversion, and you better do the two different kind of steps. What is your take on that? You think you choose the two-step approach, and the reason for that?
The main reason is that there are no to very little operational offshore wind farms in the region as of now. And given our geographical focus, we wanted to produce a tool that is relevant to this particular geographical region. So what is available to us are the wind speed measurements. We don't have wind power production. So all the wind power production values over here are actually simulated wind power production values. They are not actual wind power production values. Had we had actual wind power values, I would have modeled directly the wind power predictions, if that's obviously the end goal of the project.
Okay, all right. So Brian has a question. Brian, do you want to ask your question or you want me to read from the chat?
Yeah, I think either way is fine. Just wondering how basically if the short term is the best model for the, let's say, 0 to 4 hours, how does the ensemble outperform that during that time?
Yeah, so that's a very good question. There are two takes on that, or actually, I think there's one answer that is primarily the reason is the fact that this is. Let me show the graph that you're referring to. I believe this is the graph you're referring to, right?
Yep.
Yeah. So this is an average. So this is not just one forecasting role, right? So once you average across many forecasting roles, then the performance of AI RU-Whorf on average is better than the short-term model for the short-term horizon. And the main benefit is coming from this dynamic thresholding in the sense that sometimes the threshold that separates the improvement of the short-term model versus the long-term model is at 6 hours. Sometimes it's at 2 hours. Sometimes it's at 1 hour. So the fact that our approach is able to dynamically adapt to the degrading performance of each model over time enables us to achieve, on average, a performance that is better than the short-term model alone.
Okay, makes sense. Thank you.
Thank you.
Any other questions from the audience? I noticed you mentioned your student Feng Ye several times, and he's right now your former student, right? He himself become a professor at the Clemson University.
Yes, that's correct. He has been the lead researcher on this project. So many of the models that has been shown here has been his work, and you can see also he's the main author on many of the papers there. He is starting as a tenure track system professor at Clemson University this fall. So one of the reasons why I don't think I'm going to make it to that competition is that I lost to my best student. but we'll see.
Okay.
We'll see.
Well, you still can team up, right? I mean,
of course, yes.
He's not if there's no other questions from the audience, I have one final question for Aziz. Probably about 2 years ago, Google published the paper in either Science or Nature, I don't remember which journal. They basically claim if you have enough data, you can use a pure data-driven model to learn the pattern and to do the even longer than a couple of hours of forecasting. And they claim they can even do weeks ahead forecasting, and they were able to beat the numerical weather forecast. And with this kind of rate of the AI model going, right, I'm not really exactly talking about Gen AI, but that's different kind of direction. But with the general idea is like if you have enough data, you can learn some patterns people simply doesn't notice. And do you think the NWP eventually will become obsolete and can be replaced by pure data-driven things?
So that's a question I can answer first in the context of our project, right? In the context of our project, as I mentioned in the beginning, we were significantly limited in terms of the scarcity and the sparsity of the data sets that are available that limited our choices in which techniques we can use, right? So most brute force deep learning models were kind of like not suitable for the type of scenario that we have, in addition to our need to also produce probabilistic outputs, right? In general, what these papers show that if you have enough data, then you can beat numerical weather prediction models, right? So, and it looks like this is where the direction is heading. But I think this doesn't mean necessarily that meteorologists will be out of job, right? Because as we see here, there's a lot of important meteorological information that goes into developing these models. So there will always be a role for meteorologists to play in the development of these models.
Okay, well, thank you very much. And Two more announcements. Number one, the recording, and by the way, Aziz, please send me your slides after the talk, and will be placed on the data science for wind energy platform, the workspace, and I will send out an email to tell you when it's available. And also announcement for our September series. Professor Yingxin Bian is going to give a talk on the data science for wind energy, but it's not on forecasting. I think it's for something else. And I will send out the abstract, and the time is still the second week of Monday at the same time. Okay, and I will send out an abstract about a week before her seminar. Okay, and with that, we conclude today's seminar, and thank you very much for being here. And thank you very much, Aziz, for giving this great talk.
Thank you very much. It's my pleasure. Thank you.
Thank you.
Thank you.